Welcome to day 6 of lecture. This will be the first lecture in a series of 2, and we'll begin today by talking about blood pressure and resistance. You might be wondering, what's with the Mozart? Well, in a study conducted, a peer-reviewed study called The Cardiovascular Effect of Musical Genres, a randomized control study of the effect of compositions by Mozart, Strauss, and ABBA, they found that Mozart and Strauss can reduce blood pressure over time, while music by ABBA did not. Alright, that's ABBA for a little contrast there. I can tell my blood pressure is going up already. So, as always, pause and print if you'd like to fill out this worksheet as we move along today. Down in the bottom right, you'll see that I did put the DOI for that study I mentioned on the intro slide. And some memes, not quite science memes, they've gotten away from us, but funny nonetheless. So, with a 4-year-old child, this is what I feel like at daycare drop-off. We'll begin today by generally defining blood pressure and then looking at both the characteristics and relative pressure gradients for the arteries, the capillaries, and the veins. Alright, we're aware now that Mozart can lower blood pressure, but what is blood pressure? Well, it's the force of blood against a vessel wall. And similarly, blood pressure gradient is a change in blood pressure from one end of that vessel to the other. And gradients are important because that's what drives the blood through the vessels. So on one end, we have a high pressure, and on the other, we're going to have a lower blood pressure. Now that's a gradient. Okay, so we can see here that pressure is highest in arteries and lowest in the veins. So if we begin with arteries on our x-axis here and go up to the top of this y-axis, we have blood pressure. And we can see this is going to be around about 120 millimeters of mercury. And as we move to the veins, we'll see it drops to maybe about 40 millimeters of mercury. If we look at the bottom of this y-axis here, we'll see there are similar trends with blood velocity, although we do see an uptick again when we hit those veins and venules after leaving the capillary beds. The pressure gradient is assigned this mathematical term, a delta P, and that just symbolizes a change in pressure over the length of that vessel. That's what the gradient is. So we say here, to kind of illustrate this point a little bit better, the pressure gradient is the pressure difference between the beginning and the end of a vessel. So let's say we're talking about an artery near the heart. Well, we're going to have a higher pressure there than we will at the end of that vessel, where that pressure will be lower. And that's the pressure gradient. So blood's going to flow from the area of higher pressure to the area of lower pressure. So it's the difference between those two values. So you can subtract the low from the high, or what those pressure values may be, to find your delta P. Let's then take a minute and apply this concept of delta P. So looking at vessel 1 here, that's the top vessel, what is the pressure gradient, or delta P, for vessel 1? Well, we can see that at the start of that vessel, which would be nearest to the heart, we have 50 millimeters of mercury, and then at the end of that vessel we have 10 millimeters of mercury. So the difference between those is 40, so we have a delta P, or pressure gradient, of 40. For another question, how does the pressure gradient in vessel 2 then compare to vessel 1? Well, we see that the pressure gradient for vessel 2 would be 80. That's 90 minus 10 millimeters of mercury. And we said that we had 40 for vessel 1. So it's in fact 2 times more. If we look at an image like this that has our different vessels on the x-axis and then blood pressure on the y in millimeters of mercury, we notice a few trends, right? We see that as we move from the largest of the arteries down to the small veins and then back to the heart, we see a large pressure gradient. It continues to decrease the blood pressure as we move through the vessels away from the heart and return to the heart. The other thing we see is that up with the arteries and arterioles, we see that there is variation within that blood pressure. Now let's break this image down. Beginning with arterial blood pressure, the first thing we notice is that the blood flow within those arteries pulses with the cardiac cycle. So we see this pulsatile activity, we call it, with the blood pressure. It's rising and falling. There's variation. And we see that when the heart is in systole, or it's contracting, that is when we see the highest blood pressure generated. The higher pressure is generated in the arteries as they're being stretched. And that's the systolic pressure. Okay, that's going to be the peak of this variation here within that blood pressure. When taking arterial blood pressure then, we note the systolic pressure as the upper value within that ratio. This is followed then by the diastolic pressure that occurs when the ventricles relax, when the heart is in diastole. Okay? And we see this as the lower pressure that's generated within the arteries as they recoil. So we see this as the bottom of the trough here within that variation due to the cardiac cycle. Okay? So that's our diastolic pressure, and we record that as the lower number of that blood pressure ratio. We've all had our blood pressure taken at one point or another. Maybe it's your annual physical. So they'll slip that cuff around your arm, and here we're going to measure arterial blood pressure. So first value we're going to get is that systolic pressure that's generated when the heart is in systole. We get that ventricular contraction. And on average, that's about 120 millimeters of mercury in your average adult. And then when those arteries are recoiling and there's no ventricular contraction, when the heart is in diastole, it's relaxed, that's when we get that diastolic value. And on average, that's about 80 millimeters of mercury. So given those two values, we would say that this individual's blood pressure is 120 over 80. And this is useful because we can make a few different calculations based upon your arterial blood pressure. Now we'll look at how we can calculate pulse pressure and mean arterial pressure given our arterial blood pressure values. While arterial blood pressure is a useful measurement by itself, we can use those systolic and diastolic values to further determine pulse pressure. We define pulse pressure as the additional pressure that's placed on the arteries from when the heart is resting to when it is contracting. So when the heart is in diastole to when it is in systole. What is the difference there between those values? So given this information, I'd like you to determine the pulse pressure given a systolic pressure, arterial pressure of 120, and a diastolic pressure of 80 millimeters of mercury. A good way to think of this then, pulse pressure, is it's the pressure in the arteries that's added by the contraction of the heart. So as a baseline, we have the heart in diastole, we have our diastolic blood pressure, and then how is that going to change with a contraction of the heart when the heart is in systole? Okay, so it's the added pressure. So it equals the difference between the systolic and the diastolic blood pressures. So that gives us a pulse pressure of 40 millimeters of mercury, the difference between 120 and 80. And pulse pressure is an important value because it gives us a measurement of how elastic our arteries are, or their ability to recoil. So when we have healthy, elastic arteries, they can expand and recoil easily. Remember I showed you that example where they're kind of like a balloon. They're going to blow up, and then with that elastic property, they can then recoil, and that's going to help propel that blood forward. But as we become older and our arteries tend to harden, we see the elastic ability of the arteries that also deteriorates. So as a think, pair, share, does pulse pressure increase or decrease with age, given the little bit of information I've given you here? So pause and think about that. Well, if our arteries are hardening, then we're going to see less recoil. If we lose that ability for the vessels to recoil, we're going to see an increase in pressure, right? Those artery walls aren't going to give and expand. So we're going to see an increase in pressure with that blood pushing against it, but with no ability to accommodate that. Okay? And this is due to those hardened vessels. So as we age, our systolic generally increases. We see greater pulse pressure. So maybe we had a systolic blood pressure of 120 before. Let's say that rises to 140 now due to a greater age or losing that elastic ability. Well, to determine our pulse pressure, we'll do 140, our systolic, subtract the diastolic, 80, and we'll end up with a 60. Okay, so we're 20 millimeters of mercury higher than we were before when it was 120 minus 80. Another important value that we can determine, given our arterial blood pressure, those systolic and diastolic values, would be the mean arterial pressure, or what we'll call MAP moving forward. And MAP is the average arterial blood pressure across the entire cardiac cycle. Or in other words, it's the mean pressure of the blood pressure forces on the arteries. Now, we can't just take the average of the two values because the diastole actually lasts longer than systole. So the mean is weighted to be closer to those diastolic pressure values. And we calculate MAP as the diastolic pressure plus 1/3 of the pulse pressure. So take a minute and as a think, pair, share, calculate MAP given a blood pressure, our average blood pressure, of 120 over 80. Well, the first thing we need to do is determine this pulse pressure. And the pulse pressure, remember we said, is the difference between the systolic and the diastolic. So we'll do 120 minus 80, and that gives us a pulse pressure of 40. Okay? And then we take the diastolic pressure, which is 80, and then we add 1/3 that pulse pressure. Okay? So that's going to give us a MAP of 93. And MAP is important because it gives us this index of perfusion, or how well tissues are perfused. And healthy values would be between 70 to 110 millimeters of mercury. That indicates good perfusion. And remember that perfusion is the circulation of blood through the tissues. It's how we supply the organs or tissues with the nutrients and oxygen they need. So if we have a lower mean arterial pressure, if it's less than 60, that could indicate insufficient blood flow and inadequate perfusion of tissues. Returning to the image that we started with today, I'm going to point out a couple things. The first is now we can see this mean arterial pressure, and you really can tell that it is weighted toward diastolic pressure. It's not right in the middle of these peaks and troughs with our systolic and diastolic pressures. It's weighted more toward the diastolic pressure because, again, we're in diastole longer than we are systole, so we need to account for that. The other thing we're going to notice is that as we move away from the arteries, we lose this pulsatile activities as we move into the capillaries and veins. So the pressure is no longer fluctuating between those systolic and diastolic contractions. We see the flow and the pressure are now smooth. So as a quick thinking exercise, do we have pulse pressure anymore as we move to the capillaries and the veins? No, that's right. The pulse pressure is now gone. Because remember, to calculate pulse pressure, we'll take the difference between systolic and diastolic. They're the same. So we do not have pulse pressure any longer. But importantly, we still have a gradient. So looking at the capillaries here, if we look at the arterial end of the capillary, okay, it's about 40 millimeters of mercury. And then at the venous end of the capillary, we're around 20. So that pressure gradient still exists. Pulsatile blood pressure is gone now as we enter the capillaries. And looking at the top part of this figure in the violet, we see that we have a lower blood pressure. Okay? But this blood pressure, it's got to be high enough for the exchange of substances, being able to drive that gas exchange and nutrient exchange. However, it needs to be low enough so that we're not damaging those fragile capillaries. And as we turn to the bottom part of this figure, we see that we are also at the lowest velocity that we'll experience within the veins within those capillaries. And we'll get more into this when we talk about the specifics of capillary exchange in the next lecture. Now to looking at two ways we can help venous return, the skeletal muscle pump and the respiratory pump. Moving now to the veins, so we're going to be talking about this area here on our figure. We're talking about the movement of blood from the capillaries to the heart, and we're using the veins to do that. Those are the vessels, and we term this venous return. We're getting the blood back to the heart. And we see again that it is not pulsatile. We're too far from the heart to see those variations with the contraction and relaxation. So there's no pulse pressure again, and we see that the flow and the pressure are smooth. However, we see that there's a very small gradient that exists now. We're at about 20 here at the venules, and when we get back to the heart here at the vena cava, we're at about 0. So we have this 20 millimeters of mercury pressure gradient. But there's a small pressure gradient. So how do we overcome this insufficient pressure gradient? Because really it's the gradient that matters in order to return the blood to the heart. Well, let's look at a couple mechanisms here. While we do have that 20 millimeters of mercury pressure gradient, it's not really sufficient enough to get the blood moving through the veins back to the heart in a couple of conditions. So we need some type of assistance. And the first type of assistance we're going to talk about is called the skeletal muscle pump. And this assists in venous return from our limbs. There are many large veins that lie between our skeletal muscles. And contraction of those skeletal muscles, it compresses veins and it drives the blood forward through the veins and therefore through the valves. Okay? And the blood is pushed forward and the valves prevent backflow. So it's a great way to return blood to the heart during exercise. The increase in movement that we see during exercise, that's going to lead to increased skeletal muscle pump, and it's going to lead to increased venous return then. Okay? Here's a good depiction of what that would look like. So we can see there, when we get contraction of this skeletal muscle, we have this large vein here lying between them. It does push the blood in both directions. Perhaps that's not the best color to be using. Okay. But we have the closure of this valve here. So we have prevented the blood from moving backwards through that vein, and therefore we only see this net movement of the blood forward and back toward the heart. You can imagine then that maybe some trouble would arise if you had long periods of inactivity where we get no skeletal muscle pump action. Maybe blood is going to pool in your legs during this period of inactivity. So to help with that, one of the things you can do is wear something like compression socks. So my wife's on her feet all day, she wears these compression socks, and what they do is they gently squeeze and compress your legs to help prevent pooling within those vessels. And this will help prevent against things like deep vein thrombosis. Deep vein thrombosis, or DVT, is a term some of you may be familiar with. And that's when a blood clot forms in a vein in your body. And most of the time we're seeing these occur within your lower legs or your thighs. So let's say we have prolonged pooling of blood within a vessel in your leg. And over time, a clot or a thrombus can develop. Now the trouble with this is a deep vein thrombus, a DVT, it can break loose and cause a serious problem in the lung. And we call this a pulmonary embolism. And this is a condition in which one or more of the arteries in the lungs become blocked by a blood clot. And then we see tissue death if that area of the lung is not getting the supply of nutrients and oxygen it needs. In addition to the skeletal muscle pump, which helps with venous return in the limbs, we have the respiratory pump, which assists with venous return within the thorax. This is cool because both inspiration, breathing in, and expiration, breathing out, cause pressure gradient changes that help with venous return. And we see that increases in breathing, they also facilitate blood movement. Let's look at the mechanics of the respiratory pump. So when we breathe in or inspire, we're going to see contraction of this diaphragm. So that means it's going to flatten out. And when that happens, we're going to see a decrease in intrathoracic pressure. So within the thorax here, there's going to be a decrease in pressure, right? This area is going to get bigger, the pressure is going to drop. And simultaneously then, we're going to see an increase in intra-abdominal pressure because this diaphragm is flattening, making this area smaller. And therefore, we're going to compress these vessels that are within the abdominal cavity. And what that does is that pushes the blood upward into the thoracic cavity where we now have lower pressure. So we see an overall increase in blood flow into our thoracic veins when we breathe in. When we exhale or expire, we'll see something a little different. The diaphragm then is going to relax. Okay, take on that original resting conformation, which means there's an increase in volume within the thoracic cavity. Okay. That means with that increase in volume, there's going to be a decrease in intra-abdominal pressure, and therefore there's going to be a release of compression on those vessels that were previously compressed within the abdominal cavity. Okay. That's going to allow blood to move up into the abdominal cavity from these lower limbs. Simultaneously then, if our diaphragm is relaxing, then our thoracic cavity is getting smaller. There's a lower volume, which means there's going to be increased intrathoracic pressure. That's going to put pressure on the vessels within the thoracic cavity to drive blood into the heart. So we see then, with expiration, we're going to see an increase in blood flow into the heart and the abdominal veins. Okay, let's take a look at peripheral resistance then. Resistance, or the term R, is the measure of opposition of blood flow through a vessel. It's how much resistance that blood experiences as it's moving through one of the vessels. And it depends on three things. And the first of those is blood viscosity. So I'm just going to write viscosity here. You can put this on your worksheet if you'd like. Okay. And blood viscosity occurs due to friction between molecules during the flow of the blood. And its primary determinant is the number of red blood cells within the blood. Okay. So blood, in fact, is 4.5 times more viscous than water. So it's going to move a little slower and have a little more friction. This can be affected by things like anemia, that would be a low number of red blood cells, or your level of hydration. So if you're dehydrated, you're going to have more viscous blood. Another determinant of resistance would be vessel length. And you can imagine a longer vessel, the blood therefore is going to experience more resistance as it's moving through it. However, vessel length is pretty constant within the body, so this really isn't a factor. And the final determinant of resistance is going to be the radius of the vessel. Okay. So you can imagine with a smaller vessel, it's narrower, there's going to be more contact with the blood with that vessel surface and therefore greater resistance. So let me ask you then, of these three, which do you think is the largest contributing factor for resistance? And I should point out here, we're talking about peripheral resistance. So we're talking about resistance of blood in blood vessels as opposed to the heart. So we say peripheral resistance. Well, the major determinant of resistance to flow in a vessel is that vessel's radius. And that's because a slight change in the radius can produce great changes to blood flow. So we say that R, which is resistance, is proportional to 1 over the radius to the 4th power. Let's apply this and see why this is so. Let me try to illustrate that previous point. So here we have two vessels. And we said that resistance is equal to 1 over the radius to the 4th power. All right, so this first vessel, let's say it has a radius of 2. The second vessel, let's say it's twice that, and this has a radius of 4. Well, if we do the math here, we got 1 over 2 to the 4th. So that'll be our resistance for the first vessel. And if we calculate that out, we'll get 0.06. And do the math for our second vessel here, we have 1 over 4 to the 4th. Okay, and with that, we get 0.004. These are our two values for resistance. And you can see with that larger radius, the resistance is much lower. And if we visualize that, we can see why. Here we have 10 mils of blood. And you can see how much contact there is with the vessel wall. Right? So there's going to be lots of friction. Here is our larger vessel. And you can see with that same volume of blood, how much less contact there is with the vessel wall. So it's going to move through that larger vessel more easily with less friction. And we will finish today by looking at the relationship between total blood flow and the pressure gradients and resistance that we just looked at. In the last lecture, we finished up talking about total blood flow. So we said it's equal to cardiac output. It's the amount of blood that's moving through the entire cardiovascular system in an amount of time. And now we see it's influenced by both blood pressure gradients and resistance, the two terms that we previously described and defined here today. So we see that the relationship that exists is that blood flow is directly proportional to the pressure gradient. So that's simply saying that with increased pressure gradient, we're going to see higher flow. And we see that it's inversely proportional to vascular resistance, or greater resistance will lead to lower total blood flow. So we have our terms here. We have F, which is the flow rate of blood through a vessel, and that's proportional to the pressure gradient over our resistance. Let's apply this. Given the following information, I'd like you to calculate the relative flow rate for vessel 1 versus vessel 2. So I'm going to give you here that the radius of vessel 2 is 2 times that of vessel 1, and that they also have the same pressure gradient. Okay, so take a minute, pull out a scratch piece of paper, and see if you can come up with our relative flow rates. All right, let's work through what you got here. So we can take a look at this key down here. We know that resistance is equal to 1 over the radius to the 4th power, and then flow is proportional to, that should be a proportional sign, the pressure gradient over resistance. So we said that they have the same pressure gradient. So let's just say that's equal to 1 to keep it simple. So we'll do F equals 1, and we'll do the first vessel here, vessel 1. And that's going to be over resistance, which we said is equal to 1 over the radius to the 4th power. Again, let's just keep that simple and say the first one has a radius of 1. Okay, so we'll do that here. And when we do that math, we'll just get a value of 1 for the first vessel. Now, moving on to the second vessel here, again, we'll say that the pressure gradient is 1 for simplicity, and then we'll have 1 over 2, because it's twice the size, remember, this radius of the second vessel, 2 to the 4th. And if we do that math, 1 divided by 1, like 2 to the 4th, we end up with 16. We can see the flow rate then is 16 times that of vessel 1. Most mornings, I can totally relate with this guy. And then up in the top left, we have Throwback Thursday to when my fish that lived for 3 years died, and I didn't have a picture with it, so I made my mom take one. That photo, I bet, will live in infamy with that woman forever.